Welcome. In this first lecture of week 4, final week of our research methods course, we shall be looking at the topic of correlation. This lecture will introduce correlation analysis, which is a statistical method to examine the strength and direction of a linear relationship between two variables. The correlation coefficient, ranging from -1 to +1, quantifies this relationship. We shall also be discussing key concepts such as positive and negative correlation, significance testing, and then the distinction between Pearson correlation and Spearman's correlation. We shall emphasize that correlation does not imply causation and highlight the risk of spurious relationships. We shall also be looking at the concept of partial correlation, which is a technique that is used to control for the influence of a third variable, thereby revealing the unique association between the two primary variables that we are interested in. Correlation analysis can be calculated to investigate the linear relationship of variables. An emphasis here is on the word linear. The relationship between these two variables is assumed to be linear. How strong these variables are correlated is determined by the correlation coefficient, and that varies from -1 to +1. Correlation analysis can therefore be used to make a statement about the strength and the direction of the relationship between two variables. For example, suppose one wanted to find out the connection between height and weight. Correlation analysis can show us if these two characteristics are related, and if they are related, it implies that we can use one of them to predict the other. Therefore, if the correlation between height and weight is confirmed, it is then possible for us to predict the weight given the height using a linear regression model. If the correlation between height and weight is analyzed and a strong correlation occurs, it would be logical to assume that weight is influenced by height and not vice versa. Not vice versa. But this assumption can by no means be proven on the basis of a correlation analysis. It therefore means that any time we find a correlation, it does not necessarily mean that it is causal. So if there's a correlation between weight and height, it does not mean that weight is what is causing height. Any correlation we find should be looked at more closely, and we don't need to interpret it immediately. It is possible that a correlation between variable x, in this case height, and variable y, in this case weight, is generated by a third variable z, that is caloric intake. So therefore it means that there is a partial correlation. How do we interpret correlation? When we do a correlation analysis, we can make a statement, and that statement can tell us about the direction and the strength of the linear relationship between two scale or two ordinal variables. The direction indicates whether there is a positive correlation or a negative correlation. A positive correlation exists if larger values of variable A are accompanied by larger values of variable B. So looking at our height and weight example, we find that there is a positive correlation, and the correlation coefficient is going to lie between 0 and 1. That is, it's going to have a positive value. In contrast, a negative correlation exists if larger values of variable A are accompanied by smaller values of variable B. So there is an inverse relationship between variable A and variable B. An example of that is product price and sales quantity, and this typically has a negative correlation, because the higher the price, the smaller we're able to sell. So if the product is more expensive, then the sales quantity is going to decline, and in this case the correlation coefficient is between -1 and 0, so it assumes a negative value. So the sign tells us whether the relationship is positive or negative. How do we test correlation for significance? They can be tested using a t-test. As a rule, we test whether the correlation coefficient is significantly different from 0. That is, we test that there is linear independence. In this case, the null hypothesis is that there is no correlation between the variables under consideration. In contrast, the alternative hypothesis assumes that there is a correlation. As pointed out, we use the t-test to test correlation for significance. And we can see the formula that we use displayed on this slide. N is the sample size, R is the correlation that has been determined or calculated in the sample. And then we can determine or calculate the corresponding p-value using a t-distribution with n-2 degrees of freedom. With Pearson correlation analysis, we get a statement about the linear correlation between scale variables. And when we say scale variables, we are referring to continuous variables. The respective covariance is what is used for the calculation. The covariance gives a positive value if there's a positive correlation between the variables, and it provides us a negative value if there is a negative correlation. The covariance is calculated as follows. As we can see, it is the sum of the product of the deviation from the means of the two variables, divided by n-1. Of course, we do not expect that you will memorize this formula, but it's just to give you an idea of how the covariance is calculated. The covariance is not normalized, and it can assume values between -infinity and +infinity. And so this makes it difficult to compare the strength of relationships between different variables. For this reason, we calculate the correlation coefficient. It also has a synonym of the product moment correlation. And this is obtained by normalizing the covariance, as we see in the formula displayed on this slide. The Pearson correlation coefficient can now take values between -1 and +1. The value of +1 means that there is an entirely positive linear relationship. The more of x there is, the more of y we find. The value of -1 indicates that an entirely negative linear relationship exists. So the less, or rather the more of x that we find, the less of y that we get. With the value of 0, there is no linear relationship. That is, the variables do not have any correlation with each other at all. These plots give a visual representation of degrees of correlation. And so we see that if there is a perfect negative correlation, we're going to have the observations all on a straight line that descends. So this is perfect negative correlation. Compare with perfect positive correlation. Values are all on one line. How they are clustered around this straight line gives an idea of the strength of correlation. So for this strong negative correlation we find that the lines are clustered around that negative descent. Similarly, for strong positive correlation, they are clustered around this positive ascent. But they do not lie on the line anyway, but they are clustered around it. And for weak correlation, there is more dispersion. Same here for weak positive. So you find that the lines are much more dispersed. And for no correlation at all, it's all scattered with no pattern discernible. And so visually we can plot and have an idea of whether the correlation is present or not present. Another reason why we should plot or use scatter plots to visually check whether a linear relationship exists is this plot that we see here. In all four cases, calculating the correlation coefficient gives us the same figure. However, when you plot the data points, we find that the story is quite different. In the first of this Anscombe's quartet, we find that the correlation is given as 0.816 and the points of observation are scattered along the line. They are closely grouped but not necessarily on the same line, and so we have a positive correlation. And just below it we find a set of observations that are almost perfectly correlated, with the exception of a single point here, which is an outlier. And this outlier is what is responsible for pulling this line upward and giving the same correlation coefficient as this upper plot here. And so what this tells us when we plot is that we probably need to pay a better attention and find out why this outlier exists. It may be a data entry error which is giving us false results. And so a truer measure of the correlation may be whatever is gotten by these lines here. And then we see here that the lines are all, the observations are all on this, have the same x value, right? On the x-axis have the same value. So basically a vertical line, again with an outlying data point here, and this is what has caused the distortion. And in this particular plot we see that the relationship is curvilinear, so it's certainly not linear at all. And in this particular case, a Pearson's correlation is absolutely inappropriate and not the right statistic. So this is also one of the reasons why it's important to visualize your data. So we use scatter plots to visually check in advance whether a linear relationship exists. The Pearson correlation is only useful and purposeful if linear relationships are present. How do we interpret the strength of correlation? So with regard to the strength of the correlation, this table serves as a guide. Between 0.0 and less than 0.1, we can assume that there's no correlation. Between 0.5 and 0.7, we can say that the degree of correlation is high. And above 0.7, we can say it's a very high correlation. And so this gives us a rough guide how to interpret the strength of correlation. There are certain assumptions that underpin correlation analysis, and the first is that both variables must be normally distributed, and the second is that there must be a linear relationship between the variables. You've heard us talk about Pearson's correlation. We come to Spearman rank correlation, and we use Spearman correlation analysis to calculate relationship between two variables that have ordinal levels of measurement. So Spearman rank correlation is the non-parametric equivalent of the Pearson correlation analysis. Procedure is therefore used when the prerequisites for a Pearson correlation analysis are not met. And we already stated those two assumptions earlier. The first of which was both must be normally distributed. So if both sets of variables are not normally distributed, then we can use Spearman rank correlation. Calculation is based on ranking the data. So measured values are not used for the calculation but are transformed into ranks, and the test is then performed using these ranks. For the rank correlation coefficient, values between -1 and 1 are possible. So it has the same interpretation as the Pearson's correlation. So where rho is less than 0, it's a negative linear correlation. When it's greater than 0, it's a positive linear correlation, and when it's 0, there's no relationship. So for example, a student wants to know if there's a correlation between height, weight, and age among the participants in a statistics course. And so here's the data. It gives us 3 columns of observations on height, weight, and age. And after calculating, he gets the following figure. So the correlation between weight and height is 0.86, between age and height is 0.28, and so on, as we see on this slide. And so partial correlation helps us to calculate the correlation between two variables to the exclusion of a third variable. It makes it possible to find out whether the correlation Rxy between variables x and y is generated by the variable z. In the correlation between variable x height and variable y weight is the correlation generated by the variable z, which is caloric intake. Partial correlation helps us to be able to answer this question. The partial correlation tells us how strongly the variable x correlates with the variable y if correlation of both variables with variable x is calculated out. So in other words, we are sort of controlling for the correlation of both variables with the third variable. The formula for calculating that is given by this. Again, not that we expect you to memorize this, but it's just to give us an idea how this is arrived at. And so if we display this graphically, you see this. The correlation between x and y is only 0.329 when the correlations with x are excluded. So the correlation, the uncontrolled correlation between x and y is 0.63. But here's the point. The third variable z is influencing both variables. And so if that is not accounted for, then we misleadingly report the correlation between x and y as 0.63. However, once we account for the correlation between x and z, which is given as 0.57, and also account for the correlation between z and y, which is given as 0.88, we have the correlation between x and y given to us as 0.329. So that is a more accurate estimate, which now accounts for the influence of the third variable. Because not accounting for the influence of the third variable leads us to overestimate the correlation between x and y.